Swayam Prabha. Digital India. Educated India.
We had a reasonably long discussion on overview of experimental stress analysis, and in the last class towards the end I had also reviewed certain concepts from solid mechanics. Some of these concepts you need to brush up, and some of these concepts, though you have learned, you have to view it from a different perspective for you to apply in experimental stress analysis. And one of the first concept we looked at was the famous expression that we have for finding out principal stress direction gives you multiple answers, because you have, it is a multi-valued function and you need to know how to associate the direction of principal stress 1 to the magnitude of principal stress 1. If you go to Mohr circle, you will be able to make the relationship comfortably, but by looking at the mathematics alone you will not be able to find out. But if you have a different mathematical approach, if you coin the same problem of finding out the principal stress and its orientation as an eigenvalue and eigenvector problem, you can associate the magnitude as well as the direction. And what I said was, when you have to look at this mathematically by an appropriate approach, when we do photoelasticity, when we find out the principal stress direction, if you have to associate with maximum principal stress, we need to do an extra step, that is unavoidable. And I also said that when you go to strain gauges, you have to understand the laws of tensorial transformation. If you understand this, whole of row set analysis you can comfortably handle. Then when we come to specifying the boundary condition, I said you have all learned stress vector, you have all learned stress tensor, and what happens on a free surface, that has to be understood very clearly. And we found when you define a surface, surface is defined by an outward normal, and if the surface n is free, then we found Tn should be equal to 0, Tn should be a null vector. And we also got a very important answer on free outward corners, stress tensor also has to be 0. In fact, this understanding will go a long way even when you have to do a numerical course specifying the boundary condition and also reviewing the results presented by the numerical technique. And one more concept that I would like to show is, here you have an example of a circular disc. The disc, one of the disc is aluminum, another disc is of plastic, and what I do is I try to apply a load on this, and I would like you to ponder what would happen to both of this. I have an aluminum disc, I have an aluminum disc, and I have another disc which is made of polyurethane, and what you would see when I apply the same load, the polyurethane will deform more. And you have all have done a course in solid mechanics. I would like you to go back and then brush up your concepts and find out what would be the nature of stresses developed in these two materials. They are of the same size, and assume that they are applied to the similar load. This understanding is important when you want to apply photoelasticity. Look at introduction to photoelasticity, and once you come to photoelasticity, the important concept is light is used as a sensor. So, when it is used as a sensor, I should know what is the property of the light which is impinging on the model completely. And the equipment that you use for visualization is called a polariscope, and you essentially use polarization optics to reveal the stress information. In fact, in your earlier courses on physics, you have an introduction to what is polarization. Nevertheless, we will also look at it as part of this course, and we have also seen very clearly from a solid mechanics point of view, photoelasticity basically provides the information of sigma 1 minus sigma 2 contours. They are called isochromatics, and you also get orientation of principal stress direction at a point and also the entire model. So, at a point you will get sigma 1 minus sigma 2 as well as principal stress direction, and being a whole field technique you get this information on the entire model. And what is the physics behind this? The physics behind this is certain non-crystalline transparent materials, notably some polymeric materials, are optically isotropic under normal conditions, but become doubly refractive or birefringent when stressed. And this is a key concept. So, when you go to photoelasticity, concept of birefringence is very important, and birefringence you do not have an understanding earlier, because even in your earlier courses in physics they might have had only a passing reference, and you have to understand what is birefringence for you to appreciate photoelasticity. And how the birefringence is caused? It is caused because of the stresses that you induce on the model. So, when you analyze the polarization behavior of this, you will be in a position to go back and find out what caused this change, and hence you find out the stresses that has caused this behavior of birefringence. Birefringence in turn alters the polarization behavior of the light that passes through, because the model behaves like a crystal. So, this effect persists when the loads are maintained, but vanishes almost instantaneously or after a brief interval of time, depending on the material and conditions of loading. So, you see the birefringence under normal conditions they are isotropic, but they become doubly refractive when stressed. And how long this effect persists? As long as the loads are maintained. But later on we will also see a very special process where you could freeze this stress information by a thermal cycling process. That is different, that is very special, that has come about with material development. But when you want to do it under live load condition, what you will have to look at is the effect persists as long as the loads are maintained, and after a brief interval of time, depending on the material and conditions of loading, when the loads are removed, you do not see this effect. This is a physical characteristic on which photoelasticity is based. And when was this identified? It was identified way back in 1816 by Brewster. So, as a physical phenomena, this was identified by Brewster in 1816, but it took a long time for it to become a matured experimental technique. So, the moment you come to photoelasticity, light is important, polarization optics is important, and you need to know what is birefringence. So, what we will now see is quickly look at what is birefringence, what the term means birefringence, and then come back and then see the development, how photoelasticity is being using this concept. So, what I have here is I have a letter beam written, and the moment I put a calcite prism, I see this letters as 2. I see a beam, I see a beam on the bottom. Just see this. The moment I put a calcite prism, you see 2 images. Normally, you are used to seeing only one image in your simple lab experiment, finding out the refractive index of a glass slab, that most of you would have done in your physics course. There you would have put pins, and then you would have identified the refracted ray by putting another set of pins, and then you find out from your Snell's law, find out the refractive index. That is what you would have done. And here what you find, I place a crystal. When I place a crystal, calcite is a crystal. When I place a crystal, the word beam is seen twice, and this is because the crystal has the property of birefringence even without the application of load. The difference in photoelasticity is the model, when it is stressed, it starts behaving like a crystal. So, if I have to find out from optics point of view how the changes are related to stresses, I need to know what happens in a crystal. And what you have here is the full slide shows something which is very important. I have a light impinging on a crystal for different orientation of optic axis. How does this light behave? That is very, very important. If you understand this slide, the whole of photoelasticity is understood. And this shows a polariscope which is used for measuring the stresses, and in this case it shows the circular polariscope where I have a dark field as well as bright field, and these details you will understand as we develop the mathematics behind it. The purpose here is not just appreciate the qualitative information, but also get into quantitative analysis. And before we get into the details, let us have a brief look at what are the various branches of photoelasticity. Photoelasticity can be broadly classified into transmission and reflection photoelasticity. This we have seen, and we will also see some of these other classifications within it. And in any technique, you need to know at least briefly what was the history of development, who has contributed what, and also some timeline also you need to know, and all that we will look at now. And what you find is one of the early description on the method of photoelasticity was provided by Cocker and Philon in 1931. They had a celebrated book. Imagine 1816 the physics was identified, and as a practice it came up in 1931. And we have seen repeatedly that transmission photoelasticity is basically used for model studies and reflection photoelasticity for prototype analysis, and both of these techniques we would see in detail in this course. So, it took almost more than 100 years for the technique to develop. It takes that much time because you need technology also to help you in doing this. And you have another development which is very significant, was introduced in 1937 by Opel in Germany. What he introduced? He introduced the concept of frozen stress photoelasticity, and this was definitely a boon. See, what you find is many of the 3-dimensional problems in 1930s, when they wanted to establish the design practices, they need to find out the stresses developed on 3-dimensional components, and the concept of frozen stress photoelasticity has helped in analyzing models. And what you have here, the model undergoes a thermal cycling with the loads applied on it, and this thermal cycling helps to freeze the stresses within the model. That is the first step. You freeze the stresses within the model, and it is only a thermal cycling, it is not a freezing operation, but because it is similar to freezing, which we will also see as part of the course, why we call it a stress freezing. And the advantage you have in analysis is the loads are then removed and the model is mechanically cut into thin slices for analysis. Here again you have to slice it very carefully so that you do not introduce thermal stresses, and whatever the 2-dimensional photoelasticity you develop, you can use 2-dimensional photoelastic theory for analyzing complicated 3-dimensional models. So, what you have here is the model is stress frozen, mechanically sliced and analyzed by employing 2-dimensional concepts, and that really gave a boost. And what you need to look at is, see, whenever you find there is a development, there is a parallel criticism about it. When you are doing a mechanical slicing, in those regions where you slice it, you lose some material. So, people thought that why not I improve this process. So, this initiated people to come out with what you have is the mechanical slicing was replaced by optical slicing with the use of scattered light by Weller in 1939. So, you have another branch of photoelasticity called scattered light photoelasticity came into existence. So, this is how research proceeds. You find in the development there is a problem and that issue is researched by people, then people find out a newer technique for even doing the experiment. In scattered light photoelasticity, you basically use laser illumination. You do not use normal monochromatic light source in scattered light photoelasticity. You need to go in for laser illumination, whereas normal photoelasticity is done by your mercury arc lamp or sodium vapor lamp, which are all essentially monochromatic light sources. You do not use a laser source for the normal photoelastic experimentation, in fact it is not convenient. Then what you have, you also have other developments. 3-dimensional model as a whole was proposed by Abel in 1979. See, whatever you do, you have to pay a price. The technique is known as integrated photoelasticity. When I want to analyze the model as a whole, I have to pay my price in mathematics. When I do stress freezing and slicing, I have to pay a price in terms of more of experimentation, where I have to go mechanically slice it, but analysis becomes 2-dimensional. When you want to remove that restriction, analysis becomes mathematically challenging. So, what you have for 3-dimensional photoelasticity, you can go for scattered light photoelasticity, you can go for integrated photoelasticity or the conventional stress freezing and slicing. And what happened parallelly when all these developments were taking place, there was also extensive use of digital computers coupled with cost effective image processing system have also been developed. So, this has revolutionized photoelastic analysis in the 1990s, and a new branch of photoelasticity named digital photoelasticity emerged. So, what you have here is people have replaced human eye with an electronic eye, newer methods of processing data came into existence, and you have that branch of photoelasticity named as digital photoelasticity. In fact, these concepts could be applied to all branches of photoelasticity. We have seen transmission photoelasticity, reflection photoelasticity, scattered light photoelasticity. There are also other branches. You have photoplasticity, you have photoorthotropic elasticity, you have dynamic photoelasticity. There are too many variants, but if you understand transmission photoelasticity, the same concepts could be extended, and that is why we focus on transmission photoelasticity and reflection photoelasticity. Transmission is meant for model studies and reflection is meant for prototype in general, whereas I can apply transmission photoelasticity on glass. So, it becomes prototype analysis itself, because glass is photoelastically sensitive. And this is what you have. Technique of digital data acquisition and analysis is applicable to all branches of photoelasticity. Suitable methods and equipments have been developed over the years. So, digital photoelasticity is a generic term which implies that you use digital computers for data acquisition and processing. but as such it is applicable to all branches of photoelasticity. And what you need to do is, the moment you come to photoelasticity, you use light as a sensor, and you need to know what is the nature of light. And you have all studied all this in your physics course, it is only recapitulation of those ideas, it is nothing new, and we all know that light is an electromagnetic disturbance and it predicts two vector fields. I have an electric field and a magnetic field, and our focus is now to go and mathematically define this. So, that is what we are going to do. So, first we look at what is the light wave, and you have a electric field, you have a magnetic field, and this is the direction of propagation, and you have electric and magnetic field are in phase and mutually perpendicular. That is what is written here, the magnetic and electric vectors are in phase, perpendicular to each other and right angles to the direction of propagation. And what is my interest is, I need to go and have a mathematical description of this light. And when I want to do this, I can use either the electric vector or the magnetic field vector. And for simplicity, what I am going to do is, I am going to define the electric vector, and that is what you have it here. We will have the electric vector as the light vector, and what you need to understand is, you have an electric vector and you have a magnetic vector perpendicular to it. This is shown as an arbitrary direction, in this case electric vector is horizontal. This is shown for a generic case that I have an electric vector, I have a magnetic vector. And when you say a vector, you have a direction, you also have a magnitude. Now, I need to find out what way this happens in a natural light. That will give you an identification why we need to go for polarization optics. So, what we see here is, any light wave is electromagnetic disturbance, I have electric and magnetic field, they are mutually perpendicular, they are in phase, and you have a electric vector is used as a light vector for all our further development of photoelastic analysis. The mathematical development we will do it with electric vector. And how does this light happens in a common light source? So, that we will have to look at, and before we look at, we will also have a mathematical description, and this is nothing but a harmonic, I mean you have a sinusoidal curve. So, I can mathematically define it as, you have all seen a cos omega t and a sin omega t, it is as simple as that. And in this we bring in all the other aspects of the definition. So, I have this as a cos 2 pi by lambda c into t, and where lambda is the wavelength of light and c is the velocity of propagation, t is the time, and I can bundle this 2 pi by lambda into c as 2 pi f, and I can have this 2 pi f as omega. Either I can represent it as a cos omega t, where a is the amplitude and a cos omega t I can represent. I can also equally represent as a sin omega t. The focus here is, we want to use light as a sensor, and we want to have a mathematical description for the light, and we have seen it can have electric and magnetic vectors. Instead of electric and magnetic vectors both used at a time, we simply use the electric vector, call it as light vector, with an implicit understanding you have a magnetic vector perpendicular to it. If I have electric vector like this, I have a magnetic vector perpendicular to it and they go in phase always. So, now I have a mathematical description. Now, I go and look at how does a natural light source emits light. And I can have a magnification of this, and you see here all natural light emitters, what happens? I have a light emitted like this. We know that light can be represented by a vector, and what do you find here? Does the length of the vector remains constant? Does the orientation remain constant? Both are changing. If both the length and the direction are changing, how am I going to interpret any changes? Because I should have a constant light impinging on the model, I should know the input light characteristics, then some modification takes place within the model that modifies the property of the light that is passing through, that I should detect. So, for me to do that, I need to find out ways to send a constant source of light. I should have a monochromatic wavelength for convenience in mathematical development, but I also said you can also go in for color, white light, people have developed methodologies now. And what you have to keep in mind is the common light sources give you light vector as random as this. So, this is not convenient for you to relate whatever happens to this output light to the input light characteristics. I should have a constant input light characteristic, and that is what you have here. So, most light sources consist of a large number of randomly oriented atomic or molecular emitters. So, the light rays emitted from such a source will have no preferred orientation, and the tip of the light vector describes a random vibratory motion. So, which is inconvenient. So, I need to look at what is that I should do for the input light. For me to do that, we will have to understand what is polarization. So, a natural light source will have light emitting in this kind of arbitrary direction, the magnitude as well as the orientation changes. Suppose I constrain the tip of the light vector in a preferred manner, then I call that light is polarized. So, that is why you need polarization, because I need to have a constant property of incident light. I should have complete understanding of the characteristics of the incident light. So, for me to do that, I send a polarized beam of light, and because the model is going to behave like a crystal, this polarization behavior is changed by the model because of the stresses introduced, and I have another set of optics to find out what is exit light. So, this is how we do experiment in photoelasticity. So, in order to understand the physics behind it, I need to understand polarization, I need to understand birefringence, I need to understand a bit about crystal optics, then I will go and merge whatever the change in optics to stresses. That is how we are going to do it. So, we will take a little detour from solid mechanics, get into optics. So, we will go to polarization, we will go to crystal optics. So, that is what we are going to pay attention now. Some of it you might have done in your earlier courses, but we will look at it in a systematic fashion now. So, what you have is, suppose the tip is constrained to lie on the circumference of a circle. So, I have it is lying on a circumference of a circle, then I call this as circularly polarized. the input light characteristic is defined. I have a definition, the magnitude, what way it varies, the direction, how does it vary. In the case of a circularly polarized light, light vector magnitude does not vary, but the orientation vary. You make a reasonable sketch of it, you take your you do not have to put so many circles, indicate that you have this as a circularly polarized. And I can also have a very generic situation, instead of a circle, if it is an ellipse, then I call this as elliptically polarized. I have this in an elliptical fashion. So, our interest is, I want to see what is polarization. The tip of the light vector is forced to follow a definite law. First we saw, when it is constrained to lie on a circumference of a circle, we call it a circularly polarized. When the tip is constrained to follow on the ellipse, I call this as elliptically polarized. And why I take elliptical polarization? In the limiting case, it can become a circle. In the other limiting case, it can become a plane wave. The simplest polarization is the light vector lies in a single plane. Parallel to the given direction the wave front, it is said to be linearly or plane polarized. And what you will see later is, from a natural light you first get a linearly polarized light, then this light is converted into either a circularly polarized or elliptically polarized for the performance of your experiments. So, from polarization point of view, I can have linear polarization, elliptical polarization and circular polarization. We will choose some of this and find out how we use them in the experiment. That is why you have a plane polariscope, you have a circular polariscope. What does that indirectly imply is, in a plane polariscope you incident a plane polarized light on the model. In a circular polariscope, the incident light is circularly polarized. And if you go to optics literature, people also talk of, in polarization, what is known as handedness. We have also looked at it as the previous slide, we have labeled it as right handed and left handed, and that is defined here. If the tip of the light vector describes a counterclockwise motion, then it is said to be right handedly polarized. You can draw this on the same figure that you have drawn earlier, you do not have to draw another figure, you would draw these points in a sequence that shows this is anti-clockwise motion, and you call this as right handedly polarized. On the other hand, if it moves in a clockwise direction, you call that as left handedly polarized. You do not have to draw afresh. In the elliptical polarization, you put that dots. So, this is in a clockwise direction, it can be clockwise or anti-clockwise depending on the properties, and we will see how these light ellipses are formed. So, from polarization optics, you essentially measure the handedness, you measure the azimuth, you measure the major and minor axis of the light ellipse. These are all the properties you will measure. So, from optics point of view, you measure only the characteristic of the light ellipse, and we have to know what is a light ellipse, why a light ellipse is formed. For formation of a light ellipse, how you should have simple harmonic motions, all that we will see later. So, the next few classes we will be discussing only on optics, the solid mechanics takes the back seat, then we will come back to solid mechanics. You have to have this background for you to appreciate how photoelasticity as a methodology used. So, now we have seen what is polarization, and I have also said that polarization you get first linearly polarized light, and then only you can get circular or elliptical polarization. And how a linearly polarized light can be made? It can be obtained from various methods. I can use Polaroid sheets, I can use prism polarizer, I can get polarization by reflection, I can get polarization by scattering phenomena. In fact, it is a huge body of literature. You have people contributed on how to get polarization. You have several laws in physics developed on this issue, and you also find light waves at different regions are particularly suited for polarization by different methods. That is also seen. And what you have here is, I have the natural light, I have a Polaroid sheet, and this allows only light in a particular fashion. So, the natural light is modified because this acts like a filter, it filters out all other components, it sends only a component in this direction. So, I know what is the input light incident on the model, and we need to understand what is polarization. What I have here is, these are all Polaroid sheets, I have two identical strips, and what I do is, if I keep them in one direction, you see a light being transmitted, but when I rotate it relative to the other, progressively you find that light is cut off. You could see that now clearly, the central portion is black almost, and the edges are bright, and I repeat the same thing. So, what I have this is, so this confirms I have an individual piece, I have another individual piece which are identical. When I keep there is axis of polarization, when I keep the axis in the same direction, it still remains transparent, it allows light, but when I rotate perpendicular to that, when I change the axis, it cuts off the light that is transmitted by the first sheet. I call the first sheet as polarizer, I call the second sheet as analyzer, it analyzes the light that is coming out. We will again have a representation differently in the slide. This is just to demonstrate, because the slide is made based on these sheets, and it is also nice to see the sheet in a class like this. Okay, this is a Polaroid sheet, and the greatest advantage of this Polaroid sheet is, you have a larger field. I have brought a small sheet, you can have it for large even 1 meter length you can have. And on the other hand, when you go to prism polarizer, the field is small, and largely photoelasticity gain advantage because of this Polaroid sheets. And what you have here is, I have shown this as a H sheet polarizer, and this is a polyvinyl alcohol impregnated with iodine. That is why you have that tinge of color what you have here. And what you do this, the PVA polymer chains are stretched such that they form an array of aligned linear molecules in the material to which the iodine dopant is attached. That is how the sheet is made. So, it is essentially a polyvinyl alcohol impregnated with iodine. What they do is, they stretch it and then dope it with iodine. So, what you find here is, for you to understand these two statements, you need to know a little bit of crystal optics. So, we will again come back to this. Light component parallel to the chains is absorbed, and light component perpendicular to the chains is transmitted. So, this is how this Polaroid sheet operates, because our interest is not to have a random incident light. I want to have some control on what is the incident light. So, when I want to have some control on the incident light, I want to know its characteristics completely. So, I go and insert a polarizer, and what the polarizer does? The polarizer does, it has a random vibratory motion, it cuts off all the horizontal components, sends only the vertical component. So, the incident light characteristic is well understood. You are definitive of this input light characteristic, and this gets modified because of the model, and this we will have a look at it in a slightly different fashion. So, what we are going to do is, I have a light box and this is the screen. So, what I have is, I do not have any optical element in between. So, I see a light with certain level of intensity, and what I am going to do now is, I am going to introduce a polarizer. The moment I introduce a polarizer, the light intensity which was like this gets diminished. Can you see this? And I also, for drawing my optical diagram, I simply integrate the polarizer not as a sheet, but as a line, and this shows the direction of polarization. I said whatever the natural light I have, after this element it will have a vibration only in the vertical direction. So, that is why I put this by a line diagram, easy for us to find out and also draw, and this is how the direction of vibration. And the key point here is, we have seen earlier from the way it is manufactured, it absorbs light in the horizontal component. So, it allows only a vertical component. So, what you find, some amount of light is lost, the intensity is lost. From a natural light source, what comes to the polarizer, after the polarizer some amount is absorbed in this medium, but later on within the model whatever we do, we assume that there is no absorption of any kind, the light travels with the same intensity as such, only the polarization characteristic changes. That is really so also, it is a very reasonable approximation. And what we have done as experiment, we have put another element perpendicular to it, and we want to see when these two elements are rotated, when one element is fixed, another element is rotated, how does the intensity changes, that we could see. So, what I do is, I have another element introduced, and then I rotate this progressively and then bring it to horizontal. So, what happens? This is again physically same element as this. When I keep it perpendicular, this will send only light in the vertical component, this will allow light only in the horizontal component. So, the complete light is cut off. And this is what you had seen in the experiment, and this shows angular variation what I have. So, what I will do is, I will again have a relook at it. I have a natural light source, I see more illumination, then I introduce a polarizer, the illumination is minimized, and what I can also do is, I will just magnify this so that you can see what happens. So, when I keep the element rotated, what I have here, progressively the intensity gets diminished. So, this tells you many things. It tells you, yes, the light is polarized and the polarized light can be completely cut off, all that you can see. So, what I mention as principle, you have the demonstration right here. So, you have the advantage of a laboratory in the lecture class, and you also learn the method of representing it optically. I have a ray, I simply represent this by the axis of polarization, and then I have put another element when this is brought to the horizontal position. Now, this is a white light. I can also have a monochromatic light source. From quantitative analysis point of view, the mathematics is much simpler if I use a monochrome light source. With monochrome light source, what happens? I have a sodium vapor lamp, the illumination is brighter and the same phenomena takes place. I put a polarizer, some amount of intensity is lost, which you do not see very clearly in the screen, but you can see in the laboratory class that happens, and when I rotate it and keep it horizontal, this also becomes cut, the light is cut. So, what you understand is, as the analyzer is rotated, note the gradual diminishing of light intensity. So, what we have understood is, we have understood what is polarization, because now you have some form of 3-dimensional movies, they give you a special filter for you to see, that is different ways of doing it. One way of doing it is with polarization optics also you can do that, and we will summarize these results. And what I have is polarizer and analyzer are parallel. So, light is transmitted, whether it is monochromatic or white light source, and when polarizer and analyzer are crossed, you have the background is whatever the entire field, this is the field, I have a protractor on the Polaroid sheet. So, you will also know the angular orientation, and what I have here is the background is bright, the background is dark, and similar thing happens in this, but in actual experiment when you go and see, you will have a light tinge of blue which is not seen in this because of your color reproduction, which is recorded by a camera, then it is converted into computer, and then you put it here, then you view it, there is a difference. So, what you find here is light extinction is almost total while using a monochromatic light source. When I have a light source of single wavelength, when I put a polarizer and analyzer, light is completely cut off. Okay. In white light, when the polarizer and analyzer are crossed, one observes a light tinge of blue. What I have here is there is a light tinge of blue. If you have eye is sensitive on the experimental bench, you would see that, which is not truly reproduced in the record here, which is not faithfully recorded by the camera used. So, what you have learned today is, you have found out what is a natural light source, and we said, we also defined first, before we get into natural light source, what we looked at was, we looked at light is a sensor in photoelasticity, and we wanted to have a mathematical description. We recognize light is electromagnetic disturbance, you have electric and magnetic vector, and for the purpose of convenience, we will represent always an electric vector as a light vector, with an implicit understanding you always have a magnetic vector perpendicular to it, and from now onwards we will never use both electric and light vector as shown, they are mutually perpendicular, that is what we saw, mutual perpendicular you saw, and in fact we will have a similar situation with ordinary and extraordinary ray later. You should not confuse that issue with electromagnetic disturbance. See, if we go to a pond, I take a stone and drop it simultaneously, you have waves developed, and then you have interference takes place. That is, whenever you want to have interference, I need to have two waves. You also need two waves in photoelasticity, but the waves that they are not in phase like what you have, not in the same plane like what you have when you drop a stone on the pond. You have waves developed, they are in the same plane. In photoelasticity, you will find I will have two waves which are mutually perpendicular. So, there is a danger confusing these two waves which are perpendicular to electromagnetic disturbance. Electromagnetic disturbance means light will have always an electric vector and a magnetic vector. Once we come into photoelasticity, for the purpose of simplifying representation, we always take electric vector as light vector and we develop the mathematics, but you always understand there is a vector which is perpendicular to it always. Suppose when I have two waves, ordinary and extraordinary is perpendicular, you also have the corresponding magnetic fields which are mutually perpendicular, then it becomes representation too messy. And we have also seen the electric and magnetic vectors of a light wave are in phase, okay, but the two waves which we see in photoelasticity, they will not be in phase always. The phase difference causes all this formation of fringes, and I will also try to show a simple experiment for you to observe. Okay. So, what I will do is, I hope this camera faithfully records it. Now, what I do here is, because I can see, because I have a light here and then light falls on this and I see this, I do not know whether it will get fully recorded this, let us try. And what I have here is, I have the model. Now, I have these elements put perpendicular. So, what I have here is, I have this is dark and I have this model which is photoelastically sensitive, which is very soft material. When I apply, I can apply the load with just compression of fringes, that is too sensitive for it to see. And what I am going to do is, I am going to insert it in between, and do you see any change? There is no change, there is no load applied, the light is cut off, there is no load applied and light is cut off. Suppose I apply the load, you see some semblance of some lines appearing here. I have these two elements, I put them one over the other, they are crossed, you have this zone is dark, they are crossed, and when I keep the model in between, you will not even see the model, because it is perfectly merging with this, because I applied slight load, it shows as a silver line, but when I apply more load, you see a play of fringes, you see a play of fringes, you see a play of fringes, and that is what we are going to learn, and you will see much more clearly in my slides. This is just to show how this is obtained, so that you will see as we develop the course. Okay. And when you want to learn this, what is that we have to go? We have to go and brush up your simple understanding of what happens to light when it passes through isotropic media. And this is what you had done in your first level course on finding out refractive index. I have a slab of glass, and what I have is, I have an incident ray, and incident ray gets refracted and it also gets reflected. And what I have, I send an unpolarized beam of light, that is, representation is, I have a dot and a vertical line, I have a dot and a vertical line. If I have both of this, then I call this as unpolarized. This is a very simple, you all know, only thing what we are going to look at is, from our viewpoint, how we look at even refractive index. Okay. You know sin A by sin R, all that you know from your understanding of physics, but we will look at as ratio of velocities, that is more advantageous from photoelasticity point of view. When I look at the same concept with a different perspective, I get new insights how this could be exploited as an experimental technique. For any interference, I need two beams, and photoelasticity comes under the category of common path interferometers, and we have to understand how two beams come. Crystal optics says how two beams come, and then a change in the refractive index explains why there is a phase difference. So, what we are going to look at is, we will simply look at even Snell's law, we will review Snell's law, we will look at what is meant by refractive index, and we see the same thing with a different perspective, look at as ratios of velocities and develop our subject. And what you have to notice is, I send an unpolarized beam of light, it gets reflected as well as refracted. All the beams are in general unpolarized, and we will see entirely different when we go to a crystal. If I go to a crystal, crystal will only support polarized light within it. Even when I send an unpolarized light, it will be split into its components, you will have only polarized beam of light. So, that is the reason why we try to understand what is polarization. So, I need to understand polarization, I need to understand rudiments of crystal optics, then only I can go to understanding photoelasticity. And we will also have to develop the mathematics on why we have looked at elliptical polarization, why we are worried about a ellipse, and we will also bring in a concept of light ellipse. And you have to have a, for this the mathematical background is essentially trigonometry. You will have to understand sin A plus sin B, sin A plus B, all these trigonometric identities that you might have studied in your earlier courses. If you know this, the mathematical analysis of photoelasticity becomes very simple. You need matrix algebra and understanding of trigonometric identities, that you should be very familiar. If I say sin 2 theta, you should be able to say 2 sin theta cos theta, all those identities you need, because for the simplification you need all those simple concepts, and that is the mathematics, and we will develop quantitative extraction of data. That is the focus. It is not that just look at colorful fringes and then we have seen richness of qualitative information. So, we have developed quite a few indirect knowledge on how the stress field varies, that is equally needed, but you also need quantitative evaluation, and that is what we want to develop. In this class we have seen how to define natural light and why we need polarized beam of light and what is polarization. You have understood what is polarization, and we have looked at linearly polarized light, and we have also seen a polaroid sheet that is being used and how you get the light extinguished when I keep them crossed. When I keep them crossed, how they get extinguished. When you keep them as parallel, light is sent, but some amount of light is absorbed, that is why the intensity gets diminished. But after the polarizer till the analyzer, there is no change in the intensity, is the reasonable approximation for us to develop mathematical development, because in any scientific development there are approximations involved, and if those approximations are reasonably valid, absolutely no problem, and that is reasonably valid, because I am not having any optically absorbing elements in between. I am only working on polarization optics, and that is how we will develop. Thank you.